Hello friends, once again we are dealing with the design of hydrodynamic bearing, and it will be done by the Raimondi and Boyd chart. We know that there is no general closed form solution to the Reynolds equation. However, the approximate solution has been obtained by using electrical or numerical analogy method. Albert Raimondi and John Boyd of Westinghouse Research Laboratory have solved the Reynolds equation by using computer by iteration techniques, and they got the solution, and then the solution having a combination of unit place number which carries the design variable and performance variable. The design variables are those whose values are either given or can be controlled by the designer, while the performance variable are the variable those which tells how the design bearing will perform. So dealing with the numerical of hydrodynamic bearing, we will start this numerical. The hydrodynamic bearing has diameter and length of 100 mm. The radial load on bearing is 20 kilonewton. The journal speed is 1500 rpm. Radial clearance is 60 microns. If the viscosity of lubricant is 20 centipoise, determine the minimum oil film thickness, coefficient of friction, power lost in friction, the quantity of oil in liter per minute, and side leakage in liter per minute. For this numerical, Raimondi and Boyd chart is given where L by D ratio means length to diameter ratio is again given as 1. Then HO upon C, minimum oil film thickness to the clearance ratio. Then yes, Sommerfeld number is provided, R upon C into F, where F is a coefficient of friction. Then QRCNSL is again provided, where Q is the corresponding quantity of lubricant required, and the side leakage to the flow rate ratio is Qs upon Q is given in this numerical. So we will solve this numerical. We will write the given data. The hydrodynamic bearing has a diameter and a length of 100 mm. So the D is equal to L is equal to 100 mm. The radial load capital W is 20 kilonewton. So 20 into 10 raised to 3 Newton. The journal speed is 1500 rpm. So NS RPS is equal to rpm upon 60. So 1500 divided by 60 is equal to 25 rps. Then the radial clearance is 60 microns. So small c clearance is equal to 60 into 10 raised to 3 microns, mm. So mm we required, so we converted microns into mm. Then next one, the viscosity of lubricant is 25 centipoise. So centipoise has to be converted into Newton second per mm square. So 25 into 10 raised to minus 9 Newton second mm square. And again we can say the P, small p, bearing pressure, load per projected area means W, capital W upon small d into small l is equal to the correspondingly 20 into 10 raised to 3 divided by 100 into 100. So it is 2 Newton per mm square. The small p is there. As small p and mu is provided, we can calculate the Sommerfeld number. So Sommerfeld number capital S is equal to RC bracket square mu ns upon small p. So put the values of corresponding and then we will get the S is equal to 0.217. After finding this Sommerfeld number, we will go to the Raimondi and Boyd chart and we will find which is the solution for this numerical. So, for given numerical, L upon D is equal to 1 and capital S Sommerfeld number is equal to 0.217. Now we will look to this Raimondi and Boyd chart, and first step is that we have to locate L by D ratio. So in this first step we located L by D ratio as 1. So first step, the first column is verified as a 1 as a L by D. Then next step is that you have to locate the corresponding S from the table. So L by D ratio is 1. For that one you have to locate the S, and S is in between these two values. Okay, S is not there, exact S value is not there, but we can say the S is equal to 0.217 is located in between these two. So we have to do the linear interpolation. How to do the linear interpolation? Here L by D ratio is equal to 1 and you have to find the corresponding value of corresponding dimensionless factors, parameters by using this S value. Means indirectly we can say we have to generate the row for S is equal to 0.217. How to generate this value? By using simple linear equation. Now how to do the linear interpolation? So for that linear interpolation we will write the corresponding S values, Sommerfeld values. So the upper value corresponding S is equal to this one, and for that one we have to find HO upon C. So we will have the corresponding value. So means this is S and this is HO upon C for the upper value. Similarly for lower value S is equal to this one and correspondingly HO upon C is 0.4. So upper value and lower values you have to write, and then we have to find the intermediate unknown value. So how to find intermediate unknown value? For that one S we calculated and write down that S. What we calculated as S is equal to 0.217 and correspondingly HO upon C is unknown to us. Means here S is known and correspondingly upper value HO upon C is known. So both cases are known. Intermediate value known and HO upon C unknown. Then this is S is again known and HO upon C is unknown. So only one term is an unknown thing. So we will do the linear interpolation and we will find the corresponding HO upon C. So what we are doing? We are doing the unknown value means intermediate value minus upper value divided by lower value minus upper value for HO upon C ratios is equal to the intermediate known value minus upper value, lower value minus upper value. Hence only one equation, one unknown, we can calculate this one. So HO upon C from the above linear interpolation, we will get HO upon C is equal to 0.534, and corresponding 60 microns you have to multiply, and then HO is equal to 0.0032 mm, and that will be the minimum oil film thickness for the given hydrodynamic bearing. Only trick is that here we have to write down the corresponding S value and HO upon C values. So first known, intermediate known, unknown, what we have to find, and again lower known and lower known for the HO upon C. And then simple trick is that the intermediate unknown value minus upper value, then lower value minus upper value, again similarly is equal to the intermediate known value minus upper value, lower value minus upper value. This is a linear, simple linear interpolation, and according to that the unknown value can be calculated. Same thing we have to repeat for the corresponding calculations again. Now we will find the coefficient of friction. For coefficient of friction, we have to go the unitless parameter R upon C into F, where F is a coefficient of friction. So we will repeat the above process. We will write the corresponding S value and R upon C into F values. So upper value S is equal to, we return, and for that corresponding S, F value we have to write. So R upon C into F value we have to write. So S is equal to 0.264. For that one, R upon C into F is equal to 5.79. We return. Then intermediate value for S is equal to 0.217. The R upon C into F is unknown. Then corresponding lower value is 0.21, and corresponding R upon C into F value is 3.22. So we return this one, and how to do the linear interpolation? Again, the unknown intermediate value minus upper value, R upon C into F minus upper value, it is 5.79. Then lower value minus upper value, so divided by 3.22 minus 5.79 is equal to the corresponding S value, the intermediate value, the S is equal to 0.217 minus upper value 0.264, lower value 0.121 minus upper value 0.264, and then we can find R upon C into F, and correspondingly F, the coefficient of friction, can be calculated. So simple trick, we repeated for the R upon C into F value, and then we calculated the F. After F, we have to find the power lost in friction. So how to find the power loss in a friction? We know that the power loss in a friction is equal to 2 pi ns FWR divided by 10 raised to 6 kilowatt. So power loss is equal to 2 pi into 25 ns, and the RPS is there. Then F, what we calculated, it is 0.00539 into 20 into 10 raised to 3 Newton, and R is equal to 100 upon 2, means 50 mm, and correspondingly power loss can be calculated, and after the calculation we will get the power loss is equal to 0.3 sorry 0.932 kilowatt. I hope everybody understand this concept, the linear interpolation and the power loss due to friction. Then next one is that next quantity they require, the quantity of lubricant in liter per minute. So the quantity of lubricant can be calculated by using the unitless parameter or unitless number, the Q upon RCNSL, where Q is the flow rate or quantity of the corresponding lubricating oil. Again, for the same, we will go, we have to find this question mark, means intermediate value we have to find, which we are generating right now by linear interpolation. So again, for corresponding S is equal to 0.217, the Q upon RCNSL is a question mark. Write down the upper values, the corresponding upper values are written here. Then lower values, S is equal to 0.121 and Q upon RCNSL is equal to 4.33. Then write down the intermediate value, what we need to find out. So intermediate value minus upper value, lower value minus upper value for this corresponding factor, and is equal to S is equal to, so intermediate value minus upper value, again lower value minus upper value, and find out the corresponding QRCNSL, which is equal to 4.101. That we can calculate the corresponding Q by multiplication RCNSL into 4.101. Then after this we will get the Q is equal to 30,763.11 mm cube per second, but we need it should be into liter per minute. So we will convert first second into minutes. So 60 second is equal to 1 minute, we know. So multiplying and dividing by 60, we will get we will convert the 60 second into minutes. So we converted this into minutes. Then we have to convert this mm cube into meter cube. So by multiplication of 10 raised to minus 9, we can convert this mm cube into meter cube. Then after this we can go for the conversion again, and that will be in meter cube to liter. So we know that 1 meter cube is equal to 10 raised to 3 liter. So that has to be multiplied, and that will give you liter per minute. So 60 into 10 raised to minus 9 into 10 raised to 3 is the conversion factor for the mm cube per second to the liter per minute. So we will get the Q is equal to 1.845 liter per minute. Very easy. The side leakage can be calculated in liter per minute or in mm cube per second. So what may be the QS upon Q? What Q you are using, that will give the unit of the QS. So here we will do the first linear interpolation for the QS upon Q, and again the same method we have to write down the upper values for this one. The upper values for QS upon Q is written, then the lower values we have to write, then correspondingly intermediate value, unknown value, then upper value we have to write upper values, and again do the linear interpolation for the QS upon Q. So unknown QS upon Q minus upper value divided by the lower value of QS upon Q minus upper value is equal to the correspondingly intermediate value minus upper value, then again the lower value minus upper value, that will give you the QS upon Q. So the QS upon Q is equal to 0.5571, and then QS is equal to 0.5571 into Q, and the Q is already calculated by us in liter per minute, so we will get the QS is equal to 1.028 liter per minute. So this is the, you can say, the Raimondi and Boyd chart numerical by using linear interpolation, where unknown value, for the unknown value we have to create the new row of the solution. So simple trick is that only you have to go for the correct linear interpolation, then and then only we can solve such kind of numerical. Thank you everyone. If you are having any query, you can contact me. Stay at home, be safe. Thank you everyone.